All right, good everyone. You're welcome to this week's class. So today we'll talk about complex integration. In the last class we talked about differentiation of a complex variable. So today we'll do the integration. So if you have a complex variable, how do we carry out an integration over the complex plane? So let's say we have complex number. We denote the complex number as z, which is written as x plus iy, and we have the complex variable, so f of z, but we denote the f of z as just w. So z is the complex number, where w is the complex variable. That is a function that depends on the complex number z. So the complex number, we wrote it as x plus iy. The complex variable, we'll write it as u plus iv. Okay, so this is the notation we use for the complex variable, and this for the complex number. Now, so if you want to carry out the integration, that is the integral of a complex variable w with respect to the complex plane, we need the z. So we write the dz as dx plus i dy. Okay, so this is what I write for dz. The same way, dw is written as du plus I dv. So this means that if you want to carry out the integration of the complex variable w with respect to the complex plane z, so it's going to be integral. It's the same thing as writing f of z, because w equals f of z with respect to z, and f of z, we said we write it as u. If we write it as u plus iv, okay, if it denotes the complex variable as u plus iv, so we have f of z, and you will see the meaning of this, the meaning of representing the complex variable as u plus iv very soon when we take a simple example. Then dz, this dz, we write dz as dx, so dx plus I dy. Now if you expand this bracket, so here you have the integral of, so let's say u dx, that is u dx, then u times I dy, that is plus I u dy, plus iv times dx, so plus iv dx, then plus iv times I dy. So iv multiplied by I dy, I times I, that is I square, which is minus 1, then v dy. So we have this as minus v dy. So it means we have some parts that are real, like this, and we have some parts that are complex, like this and this. So we can take them together. Okay, so we take the real part, u dx minus v dy, and the imaginary part, u dy plus v dx. Okay, so let me go back to black. Okay, so in essence, we can write the integral of a complex variable with respect to z as, so we take the integral of the real part, u dx minus v dy, then for the imaginary part, so plus I integral, so you can say u dy, or you can start from v dx first, if you're taking dx first, but it's the same thing, plus u dy. Okay, so this integral now reduces to the integration of two real variables. So this is the first integration, and this is the second integration. So this is how we simplify the problem. So I'm going to mark this with, let me use another color. This is an important result that will make it easier for us to carry out integration of a complex variable. Let me call it equation 1 today. Okay, equation 1. Yeah. All right. Now, contour integration. So this is just a line integral in the z plane. Line integral in the complex plane. Okay, now, so let's say we have a complex plane, sorry. So we have this complex plane. So this is the real part, and this is the imaginary part. Okay, now we now have a curve. Let's say we have this curve C. Let's say this point is point A and this point is point B. So this curve is C. The name of this curve is C. Now, at each point on this curve C, so the curve is denoted as C. So at each point of the curve C, so there is the function that depends on Z. Okay, so at this, let me use another color. So at this point, at every point, okay, on the plane. But let me just take a single point, a particular point. Let's say this particular point is P. Okay, so and it depends on what the position at this point, the value at this point depends on the complex variable. Now it means if you want to obtain the function for, that is the integration for all the points right from this point A up to point B, we have to sum over all the points. We have to sum over all the points from A, okay, which is probably Z equals Z1, up to B, so where probably Z equals what? Z2, along the curve C. Along the curve C. So in essence, what we want to evaluate is, we want to evaluate the integral of the complex variable with respect to Z over the curve C. Okay, so put C here. Okay, so please take note of this C. I think it's this C. Okay, now so we carry out the contour integration over this curve C. So we'll see an example shortly. So in essence, if you are trying to evaluate, if you evaluate this type of integral in the complex plane, this is known as contour integration. It is known as contour integration. That is carrying out the integral of the complex variable with respect to the complex plane Z, so over the curve C. So that is what we refer to as contour integration. Let's take an example. All right, let's take this example. Evaluate. So this example, we'll use it to illustrate the concept. Evaluate the integral of f of z, the complex variable f of z with respect to z over c. That is, now in this case, the curve c is a straight line. Okay, now the complex variable in this case is f of z equals z minus I squared. So the straight line, the c, curve c in this case, is a straight line that runs from A to B, where at point A, z is 0, and at point B, z is 1 plus 2i. Now, if we try to sketch this over the complex plane, so if this is the imaginary part, and this is the real part, y. This is the real part, x is the real part, and y is the imaginary part. Now, the point A, they said is at z equals 0. Z equals 0, what does that mean? It means x is 0 and y is what? 0, because z is x plus iy. So if z is 0, it means x is 0 and y is what? 0, which is, let me use another color, which is this point, or let me use red. So which is this point? 0, 0. So this is point A. Then up to point B, and it's a straight line. Point B, z is 1 plus 2i. So if z is 1 plus 2i, so this is point A, and this is point B, which is z equals 1 plus 2i. Now if z is 1 plus 2i, it means x is what? 1, and y is what? 2. x is 1 and y is 2. And if this is 1 on the x, this is 1, 2, 3 on y. So when x is 1, y is 2. When x is 1, y is 2. So which is this point. And we can join the line. Okay, we can join the line. Sorry. So this is the line. Okay, this is point B, which is point A is z equals 0, and point B is z equals 1 plus 2i. Okay. Now, of course, you can notice a relationship between, since it's a straight line, you can notice a relationship between x and y. Okay, you observe that y is twice of z. Okay, when x is 0, y is 0. When x is 1, y is 2. So y is twice of z. So we're going to, this relationship may be useful later. All right. Now, so our integral, the integral of f of z, the z in this case, is the integral of z minus I. So z minus I squared, okay, dz. Now, we know that z is x plus iy. Okay, so what about z minus I squared? So z minus I squared will be x plus iy minus I, then you square it. And of course, we can write this as x plus iy minus I, x plus iy minus I, so that we expand this. So x times x, we have x squared, x times we have ixy plus ixy, that will be 2ixy. Okay, so we have done x times x. Okay, so let me do it separately. So x times x, x squared, x times iy, ixy, x times minus I. So that is b minus ix, then plus iy times x, so that is ixy, then iy times iy, that will be minus y squared, then iy times minus I, that will be plus y, then minus I times x minus ix, then minus I times plus iy. Minus times plus is minus, but I square is still minus, so that will be plus y. Then I square minus I times minus I, that will be minus 1. Minus times minus is plus, but I square is minus 1. So that this can be written as, so that z minus I raised to power 2 can be written as x squared minus y squared plus 2y. So I've done this, I've done this, I've done this and this. What is left of the real part? So minus 1. These are the real parts. Then for the imaginary parts, plus I into bracket, we have xy, another xy, that will be 2xy, 2xy. This is minus x, so that will be minus 2x. I think that's all. Yeah, I think that's all. So 2xy minus 2x for the imaginary part. And for the real part, we have x squared minus y squared plus 2y minus 1. All right. Now, so we can now substitute. So it means we can write our integral. So the integral of z minus I squared, the z, can be written as the integral of x squared minus y squared plus 2y minus 1, then plus I 2xy minus 2x. So over the complex plane dz, and dz is okay, let me write dz. Dz is dx plus I dy. Okay, but what we're going to use is we're going to use this formula, that the integral of a complex variable f of z or w, where w can be written as u, where is w? W is u plus iv, and z is x plus iy. So that integral, so we're going to use this formula, that integral can be written as integral u dx minus v dy plus I v dx plus u dy. Okay, now I think it will be better if I rewrite the formula, okay, so that we can use it. Okay, so we can, this is equation 1. Okay, so I've rewritten it. Now, so in our case, this is u and this is v. So u is x squared minus y squared plus 2y minus 1, where v is 2xy minus 2x. So this dz is the x, is u, yeah, dz is dx plus I dy. So this dz is dx plus I dy. Okay, so we now substitute into this equation 1. So our integral, the integral of z minus I squared dz, can now be written as the integral of u, which is x squared minus y squared plus 2y minus 1 dx, then minus v. V is 2xy minus 2x dy, then plus I think, okay, let me put this here. Then plus iv, which is 2xy minus 2x dx, then plus u dy. So u is x squared minus y squared plus 2y minus 1, then dy. Right? Yeah. Okay. Now, the trick we're going to use now is that we wrote something earlier, the relationship between y and z, so that we can simplify the integration. So we wrote earlier that if you look at the relationship between y and x and y, or y and x, so it is that y is 2x, y is twice of z. If you look at this line, this straight line, y is twice of what? Of x. So we're not going to use that trick to reduce, to simplify the integral. So we say y equals 2x. And if y is 2x, it means dy will be 2 dx. So it means we replace y by 2x and we replace dy by 2x. Then the limit of integration, okay, for x, because now we are going to remove y. We're going to replace y by 2x. The limit of integration will not be the limit of integration for x alone, and x varies from where? From 0 up to what? Up to 1. So range of x is from 0 to 1. Okay, so we now write the integral z minus I squared z now equals, so anywhere we see y, we replace it by 2x. So the first one is this. So we have integral x squared minus, so y squared will be 2x, which is 4x squared. So minus 4x squared, then plus 2y, that is 2 times 2x, that is 4x, then minus 1. That is the first integral, and the limit of integration will be from 0 to 1 dx. Then for the second one, minus 2xy, that is 2x times y, and y is now 2x. That will be 4. So 2xy means 2x times 2x, which is 4x squared. So 4x squared minus 2x dy. Now dy is 2 dx. So 2 times, so we can bring the 2 here, then dx. Then the third one, which is plus I, integral 2xy. We have done 2xy before, which is 4x squared, minus 2x dx, which is, we are talking about this one. Then plus the last one, this it will be, so it is similar to this. So that will be x squared minus 4x squared plus 4x minus 1. So dy is now 2, 0 to 1, 0 to 1, 0 to 1, then dx. So we're not going to do the integration separately. Okay, of course we can still simplify this because this is x squared and this is minus 4x squared. So we can write it as integral 0 to 1 minus 3x cubed, 3x squared plus 4x minus 1 dx minus, we can take the 2 outside, 0 to 1, 4x squared minus 2x dx plus I integral 0 to 1, 4x squared minus 2x dx, then plus, we can take the 2 outside as well, 0 to 1 minus 3x squared plus 4x minus 1. So we now carry out the integration. If you carry out the integration for the first one, we have minus 3x cubed over 3 plus 4x squared over 2 minus x, and the limit is from 0 to 1. For the second one, we have minus 2, then 4x cubed over 3 minus 2x squared over 2 from 0 to 1 as well. The third one plus I 4x cubed over 3 minus 2x squared over 2, which is just x squared, 0 to 1, then plus 2 minus 3x cubed over 3 plus 4x squared over 2, which is just 2x squared minus x, also from 0 to 1. Now, if you substitute for this case, for the first case, you have x minus x cubed plus 2x squared minus x cubed plus 2x squared minus x. So, let me say first term. So first term, so that will be, so if you substitute 1, then you have minus 1 plus 2 minus 1. Okay? Minus 1 plus 2 minus 1. So that will be 0. Then the lower limit is also 0. So it means this integral is just 0. Now, if you do the second term, the second term, you have minus 2 outside, then 4x cubed over 3 minus x squared. So 0 to 1 as well. So that will be minus 2 into brackets. When x is 1, that will be 4 over 3, then minus 1. So, and this will be minus 2 into brackets, 4 over 3 minus 1. I think that will be 1 over 3. And that will be minus 2 over 3. Then the third term, you have, this is the third term. So you have 4x cubed I. So I think it's going to be similar to this. Yes, without the 2. So it's just going to be 1, I think minus, no, I think it should be 1 over 3. Yeah, it should be 1 over 3. Because it will be 4 over 3 minus 1, which is 1 over 3. So the third term is 1 over 3 I. And the fourth term is this. So it's going to give us 0. It's similar to this term. So it's going to be 0. So therefore, the integral of z minus I squared, the z, is going to be this minus 2 over 3 plus 1 over 3i. So minus 2 over 3 plus 1 over 3i. So that is the solution to the integration. Alright. Now, the next thing I'll talk about is the Cauchy's theorem. So this Cauchy's theorem is useful when we have under certain circumstances, certain situations. So let me state the theorem first. So this is an important theorem. It states that if the complex variable f of z is regular at every point within and on a closed curve C, closed curve. So that is the essence of this circle over the integral. The circle over the integral indicates that it's a closed curve. Okay, the curve is a closed one, and we'll see an example shortly. So that the integral is going to be what? 0. Okay, the integral is going to be 0. Now, let's take an example to verify this Cauchy's theorem. So, example. Alright, so the example says, verify Cauchy's theorem by evaluating the integral of f of z, the complex variable f of z, over the complex plane z, along a closed curve C, where f of z is z squared, around the square formed by joining the points given. So the points given will actually, at the end of the day, be a square. So what we mean is that if you draw your curve, so if this is x, which is the real part, and this is the y, which is the imaginary part of the complex plane. Now, this is saying that the first point is at z equals 2. Z equals 2 means what? Means x is 2. The first point is this one, z equals 1. Okay? And this means that if z is 1, so let me write it, if z equals 1, it means x is 1 and y is what? 0. So the real part is 1 and the imaginary part is what? 0. So where do we have that here? So let's say this is 1, this is 2, this is 3, this is 4. So 1, 2, 3, 4. And here as well, this is 1, this is 2. Okay. So the first point is that x is 1, y is 0. X is 1, y is 0 is there. So this is 0. So x is 1, y is 0. This is the point. Then the second point, z is 2. It means x is 2, y is what? 0. X is 2, y is still 0. This is the second point. So we can join the points. Let me use blue. I'll use blue later to join the points. Blue color. Now, the third point is z equals 2 plus I. 2 plus I means x is 2 and y is what? Y is 1. So, x is 2, still at 2, but y has now moved to 1, this point. Then the last point is z equals 1 plus I. So that is x is 1 and y is 1. So x is 1 and y is 1, which is this point. So let's join the points. Okay, so it goes from here to this point, then to this point. So this is points A, B, C, D. Okay, yeah. Now, so what we do is, again, to refresh your mind, x is I plus IY, and the Z is going to be the x plus I dy. Now, in this case, the complex variable in this case, f of z, is z squared. Okay, it's given us z squared here, z squared. So we need z squared. So z squared is going to be x plus iy, then squared. And that will be x squared minus y squared plus 2i xy. Okay, now the integration over the closed curve C, we know that the answer is 0, but we want to verify it. F of z, the z, in this case is going to be f of z is z squared, the z. Now, and we have written z squared to be what? To be x squared minus y squared plus 2i xy. Then the z is dx plus I dy. Again, if you use our equation 1, equation 1, where we said it's the integral of u plus iv is dx plus I dy multiplied by dx equals u dx minus v dy plus iv dx. So if you use that formula here as well, so we have that this integral can be written as the integral over the closed curve C of x squared minus y squared dx minus 2xy dy, then the imaginary part 2xy dx, then plus x squared minus y squared dy, because in this case x squared minus y squared is now u, then 2xy is v. Okay, so u is x squared minus y squared and v is 2xy. Okay, so you substitute. So we now take for each side, that is for each point from A to B. Okay, so from A to B, so AB. Now at AB, what is y does not change. Y is 0 and dy is also 0. So y is 0 and dy is also what? 0, because there's no change in y. In fact, y is 0, y1 is 0, y at point B is 0, y at point A is also what? 0. So it means in our integration, we drop the terms with respect to y, the integration with respect to y, like this term, we drop it, okay, and this term, we'll drop this term, we'll drop this term, then we'll be left with this term and this, okay. Now for this term, y is also 0, so we remove this y, so that this integral, okay, this, what we'll be left with is the integral of, we are left with x squared dx here. In this case, y is 0, so y is multiplying everything. In this case, y is also 0. Okay, so this term is gone. Now, the limit of integration for the AB, x is from 1 to 2. So the limit of integration will be from 1 to 2. So 1 to 2. And if you do the integration, you have x cubed over 3 from 1 to 2. So substitute 2 raised to the power 3 over 3 minus 1 raised to the power 3 over 3. That will be 8 over 3 minus 1 over 3, and that will be 7 over 3. That's the AB. What's the next one? The next one is BC. Okay, from B to C. Now, from B to C, x does not change. That is, the x is 0. Okay, if you look at it, x remains at what? At 2. X is 2 at point B. X is also 2 at point C. So, the limit of integration for x at that point, that the dx is 0, okay, but x remains the same. Okay, so x is just 2. It remains the same. It's 2. Okay, x at point A is 2. X at point B is 2. So the dx is x at point A minus x at point B, which is x at point B minus x at point A, which is what? Which is 2 minus 2, which is 0. So dx in essence is what? Is 0, whereas x is just what? 2. So in this case, the limit of integration will be for f of z, dz, and what we do now again is this dx term, the dx term will go. So this term will go. So let me remove. Okay. So the terms that will go, this term will go. It will be 0 because dx is 0. This term will also go. It will be 0 because the x is 0. So you will be left with minus 2xy dy, then plus I x squared minus x squared dy. But x is 2. Okay, so if x is 2, it means this will be 2 squared, which is 4. Okay, so we have integral 4 minus y squared. Sorry, this term is gone. So we are considering this term. So let me use red for the terms we are considering. We're considering the terms red. Now, 2xy. So we have to delete this. Alright, so we have minus 2x, which is 2, that will be 4, then y, dy, then the other term is x squared minus y squared, so we have to put plus I integral, so x squared, which is 2 squared, okay, x is 2, so that will be 2 squared, that will be 4 minus y squared dy. Okay, now the limit of integration we know is with respect to y. So how does y change here? Okay, how does y change from b to c? At b, y is 0. At c, y is 1. So the limit of integration will be from 0 to 1. From 0 to 1. From 0 to 1. Now if you do the integration, you have minus 4y squared over 2, which will be minus 2y squared, 0 to 1. Then plus I 4y minus y cubed over 3. Then again from 0 to 1. And if you do the arithmetic, you obtain minus 2 plus 11 over 3i. Okay. Now, the next is, we have done AB, we have done BC. So next is CD. Now, for CD, the x does not change. Y does not change. Because y at C is 1. Y at D is also what? 1. So dy is 0. But the value of y is what? Is 1. Now, x now changes from 2 to 1. So the limit of integration of x at point C to D will be 2 to 1. Okay, so CD now. CD. Y remains 1. The y does not change. Okay, 0. So that the integral for the CD case, which is f of z dz, will be, so what you do is dy, all the terms with dy will be 0. Okay, so this will be 0, this term will be 0, this term will also be 0. So you now consider this one with, so this 2xy dx and x squared minus y squared dx. Now, if you carry out the arithmetic, you obtain integral 2 to 1. I told you the limit of integration will be from 2 to 1. Okay, x is 2 at point C, while x is 1 at point D. So it's going to be from 2 to 1. Then you'll be left with x squared minus 1 dx plus I integral 2 to 1 2x dx. And if you carry out the integration again, you obtain minus 4 over 3 minus 3i. Now, the last part, which is dA. So this dA. dA, y changes from 1 to 0. 1 to 0. So, but x does not change. So it means the x is going to be what? 0. While the limit of integration, why the value of x is just going to be 1. But the x is 0. Then the limit of integration with respect to y will be from 1 to 0. 1 to 0. So in this case, the integral at point D to A, f of z dz, will be from 1 to 0. Okay, then the remaining terms will be 2 minus 2y dy plus I integral 1 to 0, 1 minus y squared dy. So that you have, if you carry out the integration, you have 1 minus 2 over 3i. Now you now collect all the terms together, that is AB. So you add, so the integral in general of the function given will be at AB plus at BC plus at CD, then plus at DA. Now at AB we got 7 over 3. Then at BC we got minus 2 plus minus, sorry. Okay, yes, okay, plus minus 2 plus 11 over 3i. Then CD we got minus 4 over 3 minus 3i. Minus 4 over 3 minus 3i. Then the last term, which is plus 1 minus 2 over 3i. And if you add this, you're going to get what? 0. So this confirms Cauchy's theorem. Okay, it confirms Cauchy's theorem. All right, so I think this is where we'll stop for today. So I will see you next class. Bye for now.